Welcome back to the show. Today we are joined by Professor Henning Budde to discuss all things exercise neuroscience. Henning is a professor for sports science and research methodology at the Medical School Hamburg. He has taught and researched at a number of universities throughout Europe, in South Korea and in Australia, all the while publishing over 120 peer-reviewed articles on exercise neuroscience. Henning has accomplished these remarkable feats which, when you consider that he has a neurological disease which affects the way he speaks, are all the more remarkable indeed. In today's discussion, we deep dive into the effects of exercise on the brain. We explore how exercise promotes better cognitive functioning and delays cognitive decline. We explore what the key neurotransmitters are that are implicated in the exercise effect on mental health, and what the key reward molecules are that are involved in exercise, and much, much more. If today's episode of the Mental Wellbeing College brings value to your life, we would be super grateful if you were to hit subscribe, follow, or to share this episode with someone that you love. This is how we continue to grow the show and communicate evidence-based science and psychology out to the broader community, and communicate actionable tips so people can improve their mental health. Thanks so much for tuning in. I really hope you enjoy and get a lot of value out of today's deep dive on exercise neuroscience with Professor Henning Budde. Professor Henning Budde, welcome to the Mental Wellbeing College.
Yeah, welcome.
It's fantastic to have you on. We're going to be talking all things exercise neuroscience, which is, well, I'm glad to have a real expert in the field such as you on, Henning, given this seems like a bit of a minefield at times reading through. There's a lot of hypotheses, there's a lot of different potential explanations, but it feels like we have to be careful with the language and the level of certainty we use around why and what mechanisms are responsible for the effect of exercise on mental health. So to have an expert like you go through this is very appreciated.
Yeah, as scientists, we always have to watch our languages,
Yeah. And yeah, exactly. And certainly feel free to let me know if I'm being too certain with my language, because I know that there's, again, a lot of hypotheses, but little certainty on something. So, yeah.
Yeah.
Well, one of the hypotheses as to why exercise has the effect on mental health that it does is the monoamine hypothesis. So monoamines being a particular group of neurotransmitters, things like serotonin, noradrenaline, dopamine, and this is one of the reasons why exercise is hypothesized to have, for example, an antidepressant effect. Can you talk to us a little bit about the evidence for the monoamine hypothesis and why exercise may or may not have an impact on this particular class of neurotransmitters?
Yeah, so it's already from the early 1900s, we have the positive effect of exercise on mental health. And it's from that point on, it's always discussed why it was so helpful. And exercise has an impact on all these monoamines, like you described, and it also has an impact, of course, on mental health. So people having this effects from these studies in mind, they thought to themselves, okay, why must there not be a link between them? And of course, most of the data comes from cross-sectional studies, which makes it difficult to say if it's really the reason of it, but this is probably why it came up.
So when you say cross-sectional data, we're talking, for example, people who exercise chronically or regularly may have increases in serotonin, but there are some mixed findings there even, as I understand it.
Cross-sectional data means all the data where I just have one measurement point and don't have like a longer time where I can observe somebody. And this means at one time point, I find people have higher serotonin levels, and also the guys where make very nice statistics that correlates very nice with physical activity level, and which is also high. And then you have a very nice link that people who are active have a nice elevation in serotonin level, but you don't know if it's like because of this or probably due to another reason. Yeah.
Yeah, okay. And this comes back to, I suppose, one of the leading hypotheses of depression itself. And again, there's a lot of unknown, a lot of gray area. There isn't one unified hypothesis for why depression occurs, but serotonin, one of the monoamines, being strongly implicated or hypothesized to be implicated in the cause of depression. So if exercise increases that, then potentially that explains potentially the antidepressant effect of exercise. Is that the kind of link there?
Yeah, this is the same. In earlier times, they already detected that people have a lower amount of serotonin, and people who have a lower level of physical activity, they were also scoring with this. And so they had the link of serotonin being responsible. But nowadays they find that, of course, I also agree on that it's too simple to really say that one monoamine is responsible for all the mess that depression makes. So there are probably a lot more monoamines or other hormones or catecholamines responsible for this, and together with this impact on the brain plasticity that exercise has, it's probably very difficult to explain all that.
Yeah. Okay. So you mentioned there, Henning, catecholamines as well. So we're talking, for example, noradrenaline, dopamine. Can you talk to us a little bit about why they are potentially implicated in depression and the impact of exercise on the particular catecholamines of noradrenaline and dopamine?
Yeah, it's like, of course, dopamine is all about, all of us think about dopamine and that it has a very nice effect of, if you think of the nucleus accumbens, where it has a very nice effect when you have a high amount of release of dopamine in this area. And of course, if you have that over a certain time, you might not feel as depressive as you are. So you feel better. And this is occurring due to many kinds of stimulation you might think of. If it is exercise or sex or drugs or everything is has an impact on the dopamine system, and also is responsible for the high that people might experience, and which of course dampens the your depressive guy or your depressive episode.
Yeah. Okay. So this, you're kind of referring there to the antidepressant and anxiolytic effects of exercise that people might feel, and the runner's high that's kind of been reported from exercise. So dopamine potentially implicated in those effects from exercise.
Yeah, of course. Dopamine, of course, has an impact on all of that, and also noradrenaline. What you also said, and it has special medications like not SSRE, not selective serotonin reuptake inhibitors, but selective noradrenaline reuptake inhibitors. Are also antidepressive medications and also have an effect in some people. That's why it's sold, and I think for some people it might also work, of course.
Yeah, it's interesting as well. You bring up the SSRIs because obviously they are one of the leading kind of treatments for depression. But then on the other hand, there seems to be a bit of a lag in symptoms, or at least in symptom reduction, right? Between when someone takes an SSRI, there's a synaptic effect pretty immediately, but this reduction in symptoms doesn't occur often for a couple of weeks. So potentially serotonin itself isn't the only causal factor there. There are other things occurring which explain that lag.
Yeah, you are on the one hand side, you are experiencing these positive effects of some people at least, and who take this SSRI and who report a reduction in their depression or depressive symptoms. And yeah, but it's of course, serotonin is not the only guy who's responsible for this. Yeah. There's probably a huge line. I'm also a big fan of these BDNF you also talked about, and so this growth factors which are in the brain and who change the brain actually, and who are responsible for this neuroplasticity. They also play a big role in reducing depression, I think.
Yeah. So BDNF, that's also one of the leading hypotheses, and I certainly want to get to that shortly. So if we look at the chronic effect of exercise on monoamines, so let's stick with serotonin, dopamine, noradrenaline. Does chronic exercise or consistent exercise for weeks, months on end, does that increase these three particular monoamines?
Oh, okay. Yeah, this is actually the complete most difficult question people experience, and because you always have acute effects of monoamines, and then you have chronic effects of exercise on mental health issues. But it's very difficult to mix that up. So if you have acute, most of the hormones and catecholamines, they always go up. So you have stimulation due to acute exercise, but if you look at chronic exercise, we are speaking of something which isn't acute, but it's done more often than acute. Actually, if you do something 2 times, I don't know if you will have something that's difficult to describe if you are talking about chronic or acute, but most chronic studies will go over 3 months, I think, and then it's really difficult to achieve all the changes you thought first when you did an acute exercise. For example, you would think of reduction or attenuation of the effects which are due to an acute exercise. So you think if the body detects that somebody gives you a stimulus all over the time, every day, then of course it will shut down the reaction or dampen the reaction. So makes the reaction not be so profound that it used to be. And then after 3 months of time, you have at least lower level of or attenuate response than you had when you just had when you just think of an acute stimulus.
Yeah, it speaks to an important distinction there, right, in terms of distinguishing between the acute effect and the chronic effect, because just because something increases after one single bout of exercise doesn't mean it's going to be the same effect after repeated amounts of exercise.
Yeah, of course. And this is just to be exact in this and just watch your language in this kind of talk is very important because to differentiate between physical activity and exercise and sport, if you think about that, if this is difficult to define what is sport, and you have exercise. We don't have exercise, the expression exercise in German language, so it's difficult what you are really referring to, and all these activity levels can be acute and also can be chronic. So it's really important to at first define what you are talking about and then see what effects you can achieve.
Yeah. So, in terms of effects and measuring these effects, one particular theme I think that's going to come up throughout our conversation and certainly comes up through reading through the literature is the measurement of these neurotransmitters, for example, and where they're measured. So a lot of this is done in the peripheral nervous system, in blood, plasma, serum, but measuring neurotransmitter activity in blood doesn't necessarily translate to what's happening in the brain because of the blood-brain barrier. Can you talk to us about the importance of that and why that's an important consideration to understand what effect exercise is actually having on us in the brain?
Yeah, it's actually very important, and it's good that we are talking about that. So, for example, with when people talk about my disease, so it's I have a nerval disease, which of course is already something you would detect in the brain. Therefore, it's of course important that medication against this will differ or will go through the blood-brain barrier. So people always say, for example, in this, you also refer to this endorphin hypothesis. Endorphins probably are secreted mostly from the adrenal gland, which is it's on top of your kidneys on both sides, and it's actually not crossing the blood-brain barrier. So you probably measure something in the blood in your arm, and you don't know if it's really the same amount of concentration than you have in the brain. So it's probably two substances you're talking about, nearly. And that's why you probably also have the saliva, where you probably also can detect changes, or even in the hair. So something is detectable through there. And also, if you want to make experiments, you also have to see, for example, if I'm just taking blood from somebody, and I want to measure the input on his stress response, for example, then of course I'm stressing somebody. For example, because it hurts when you penetrate the skin, and therefore it's sometimes better if you go back and measure something, for example, in the saliva, and when you probably have the possibilities to detect changes there too. Or you can also go in the spinal fluid and detect something there. Um, this is, this is of course only doable by somebody who has an MD, and yeah.
So just to clarify then, if you're measuring saliva, is that a direct measurement of what's going on in the central nervous system, or is that more indicative of the peripheral nervous system?
It's always something that's of course not as direct, but it's also possible. For example, the adrenaline. You can also detect in the saliva vises alpha amylase, alpha amylase. This, if you start exercising and do something, it increases really rapidly. But as soon as you stop exercising, it goes down again. And while, for example, if you exercise and you measure the cortisol level, what's also doable in the saliva, where you also measure the free form, then you just need to exercise for 20 minutes or something to detect something. Or you exercise for 10 minutes and wait 10 minutes and then you can detect cortisol, because you were active in the first 10 minutes. Yeah.
Okay. Yeah, okay, that makes sense. So then I suppose it begs the question for someone as naive as myself, why not just directly measure things in the brain? Do we have the technology to do that?
Yes and no. You, of course, have the possibility to do some fMRI scans, which is like the functional detection of changes in activation of different brain areas. For example, due to a test you do in the scanner, and you watch at the screen and detect something, or you don't detect it, and then you can of course see changes in the brain, and you can refer to the area where it is, and then you can, due to this area, you can refer to the critical amine, which is mostly or have the most receptors in the area. And you can also measure the PET, which is positron emission tomography, and they can also measure something like dopamine secretion, and measure that due to, I think, you have a slightly radioactivity marker, and you will give that to the person, and yeah.
Yeah, okay.
But otherwise, it's very difficult. It's
Yeah, I think this will certainly come up as we move towards the endorphin theory, because you already alluded to it, Henning, about whether endorphins can or cannot cross the the blood-brain barrier. So let's discuss endorphins and let's take it back a little bit. So the endorphin theory, endorphins being a class of endogenous opioids. This is one of the most commonly cited theories in lay circles, that endorphins are responsible for the mood-enhancing effects of exercise, the anxiolytic effects of exercise, why we feel good when we exercise, or at least after. Now, talk to us, Henning, about why that isn't quite as straightforward as one might seem.
This is a theory which came up in the 80s, and we measured, I think it was in animal research, that mice or rodents, I don't recall, they had an elevation in endorphins, and they also were on the behavioral level some kinds like not so anxious anymore towards other animals or towards predators. And right now we are just experiencing that people are more and more see that it probably is not so easy. Then you have an elevation in something like endorphins, and then you experience something like runner's high. I mean, this would be very nice, would be totally logical, but it's unfortunately not so easy in science that you have an elevation and you can explain that due to another elevation. So it's probably I was when I was preparing for this talk, I read a nice paper of a colleague. It was published in Psychoneuroendocrinology, and this was also by a guy working in Hamburg, where I also work, but another university, and they were giving naldroxol, which is naldroxol, I think it's in English. And this,
I think naltrexone or naloxone, I think is the English.
Yeah. And exactly. And this is a medicine which blocks receptors, and therefore you have when you start exercising and do, for example, a longer run, and you have taken the medicine, and then people they took the medicine, but they experienced something like runner's high. So on the theoretical basis, you couldn't explain that due to endorphins, and so people thought about that there might be something else, and then they came along the endocannabinoid system, and because due to different kinds of actually, they started with describing the system exactly like the guys 20 years before or 40 years before, when they were in the 80s. And because they found, okay, this kind of acute exercise already elevates the hormones, and that's why they probably are responsible. And nowadays they can say, okay, probably it's not the endorphins, but there's something which is still capable of this elevation, and this is endorphins, and so they must be in a way responsible for that.
Hello everyone, a quick break from today's episode. At the Mental Wellbeing College, we are committed to the goal of communicating evidence-based wellbeing strategies out to the broader community. The goal of this podcast is to bridge a gap between self-help material and peer-reviewed research by providing evidence-based discussion that respects the nuances of psychology but is digestible for all audiences. Ultimately, I hope that you as a listener feel empowered after each episode so that you can take away and implement strategies to improve your own mental well-being. If you have gained value from this episode of the Mental Wellbeing College, I would be so grateful if you were to hit subscribe or follow, or to share this episode with someone that you love. This is how we continue to grow the show, get the message out, and to impact people in need by providing such information and strategies. Thanks so much for tuning in. It means a lot to us here at the Mental Wellbeing College. And now back to today's episode. Yeah, it's a really interesting literature. So, my reading of it is, like you said that the endorphins in the peripheral nervous system do increase after exercise, generally speaking. But then are they lipophilic? Can they cross the blood-brain barrier? It seems not. And most of the work does measure it in the peripheral nervous system. And then, like you said, when you inject or give people naloxone or naltrexone, which is that opioid receptor antagonist, theoretically, if endorphins are solely responsible for the runner's high or the anxiolytic effect, if you're blocking the effect of that in the brain, you shouldn't experience the runner's high or the anxiolytic effect. Yet people still do experience those effects even when they're given the opioid receptor antagonist. So this suggests, that endorphins aren't solely responsible, at least, for those effects. But have you seen, there's one study by, I think, another German, Boeker, Boeker, 2008, where they did PET scans of runners who they'd ran for like 2 hours, but it was about 10 runners, very well trained, and did see an increase in activity related to endorphins directly in the brain. So does that evidence would potentially suggest that exercise is causing endorphin activity in the brain? I don't know if you've seen that at all.
This is a problem with science. You always observe a change and you explain that, and this is of course not incorrect, like the colleague did, and I'm not destroying the effects he would just observe. I think it makes sense, but probably it's only good that others did experience something else, so that really a nice discussion can pop up, and that somehow I think they're not, the endorphins are probably also not solely responsible for the runner's high, and probably Mother Nature has something nice and difficult for us to think of.
Definitely, yeah. And I mean, this speaks to like the heterogeneity of exercise itself, right? I mean, number one, there are so many different forms of exercise. Number two, so many different mental illnesses, but also like it may just be that there are different mechanisms for different mental illnesses or different effects, right? Even if you look at depression, there's different forms of depression. Two people with depression can have very different symptoms. So it may just be that there are multiple mechanisms happening.
It's a very difficult field, and there's so much potential for further research, because nowadays it becomes more and more interesting, or the people are just experiencing that probably exercise did have or does have an impact. I mean, in the 80s, except for this endorphin hypothesis, people won't care about if somebody was exercising. Okay, this was something which probably is good for obesity, but it's a very nice field, and there's so much potential, even if you manipulate the way you were exercising. I mean, if you are doing endurance exercise or strength exercise, has of course a totally different outcome.
Yeah, that's so true. It's a really good point about different types of exercise as well. So, you mentioned as well, Henning, endocannabinoids. So, I don't think this is it's a particular class of reward molecules, but certainly one that I think people will be less familiar with compared to, say, endorphins or endogenous opioids.
Yeah, it's endocannabinoids are probably something which my pot smoking uh, roommate hadn't in mind when he was referring about the goodness of pot smoking. I mean, just means you have cannabinoids you are just making yourself. And of course, if you make something yourself, due to, of course, different genetic, you also have the genes to do so, and you're producing those endorphins. And if you produce something yourself, it's really nice if you have certain receptors for this, and you also can say these receptors are probably busy, or they're not busy, or you um, have a response due to your receptor bindings. These cannabinoids, due to exercise, they of course mostly rise. I mean, there's a very nice piece of literature of my Spanish PhD student, and she conducted. She's called Sandra. Fernandez, and she has a double name, which I always have difficulties in remembering. But I'm the second author, and this is a very nice paper which sums up the effects on each cannabinoid, because there are, of course, several, not just one or two, and they act via different receptors, which are also more than one, but I think not too many. And they can, when you have a look on this paper, you can see, but most certainly all of them go up when you exercise acutely.
Interestingly, as I understand it, some of the work in rodents where you have knockout mice or so cannabinoid receptor is knocked out, or you inject them with endocannabinoid antagonist drugs, so almost the equivalent of what we see with naloxone or naltrexone. The anxiolytic effect, at least in these animal models, is actually reduced. So what we hoped you would see with endorphins but don't see, which is anxiolytic effect, still occurs even when the opioid receptor antagonist drug is taken for endogenous opioids. You actually do see this with endocannabinoids, in that the anxiolytic effect is reduced in these particular circumstances.
Yeah, you probably, if you look at this paper by my Hamburg colleague in psychoneuroendocrinology, they planned actually a study what you described, and they did that before that in rodents, where they were wanted to block your cannabinoid receptors, and they probably see the same. Then they want to see when they were blocking the opioid or the endorphin receptors, but this drug is not available anymore for humans. They took it off the market, and therefore, of course, the design of the study or the results of the study from the rodents, they still have that, and they won't probably give it away, but they saw exactly what you were referring to. So if you block the receptors, the mice, of course, had a different approach to a predator, or I don't know which tests they did than if they didn't block the receptors.
Okay, so we've talked about endorphins, endocannabinoids. My summary of that is still a lot of gaps, a lot to be known, but at least as of now, it seems as though endogenous opioids aren't solely responsible for the mood-enhancing effects. Potentially, endocannabinoids have a large impact, but it's really a watch this space. But overall, the endorphin theory just isn't as certain as perhaps people talk about it in lay circles. Is that your take and your summary as well?
My summary is the time of the of the 80s theory of the endorphins is over, and so the endorphin theory is probably when you're talking about muscle soreness and say that this is related to the amount of lactate, it's probably the same. Then you were referring to the runner's high and the endorphins. I think, you probably would discuss it another time, but this is, of course, not even close to explain this theory.
Yeah. Yeah. Okay. Yeah. Perfect. Yeah. I think that's a lot for people to stew on because, again, probably something they won't have heard of and will have just bought into the endorphin hypothesis and theory. So, yeah, it's a good little debate for people to have a read into some of those papers as well. Let's talk about the HPA axis. So, this is another again, theory and hypothesized theory as to the mechanisms of why exercise might have the positive mental health impact, and the HPA axis being a coordination of the hypothalamus, pituitary gland, and adrenal gland. Can you tell us a little bit about what this theory is, what it's responsible for, and its relation to exercise?
Yeah, this axis probably has, of course, two waves. One I was already referring to. You can detect with alpha amylase. So this increase detectable right away. And then you have a second wave, which is probably a little bit slower. This is when you are stressed. So exercise is not what you probably wrote in the yellow press. I don't know a good example from Australia, but that people are saying, you are so stressed, do some exercise. And of course, an acute exercise is not something else, but it is an actual stressor. So your cortisol or your adrenaline goes up, way up. And but if you do that chronically for a longer time, then your HPA axis probably adapts to that, and probably don't react with the same amount of cortisol release due to a similar stressor. So over a longer period of time, say 3 months, with the same detection, with the same stimulation due to acute exercise, you will have lower cortisol response at the end of the treatment.
So this is the normalization of the HPA axis, that after being trained or trained participants who exercise regularly show a more attenuated response or HPA axis response post-exercise compared to those who don't exercise regularly. Now, that's important because of the role of HPA in mental illness, for example, in depression. Can you talk to us about the level of activity that we might see in people with depression, for example, in the HPA axis, and why that relates to the normalization of the HPA axis after exercise?
Yeah, this is also something which is very difficult. You have seen some elevation and also some attenuation. So both. So like always, I just think probably from my point of view, I would say that a blunted cortisol response would be something which would be more logical to me. But I'm not aware of any closing story or any which gives it or which ends this discussion which is going on forever.
Yeah, it seems to be that there's a fair amount of correlations between hyperactive HPA axis in people with depression, although, like you alluded to, some work has also shown a hyporeactive HPA axis.
What you saw and what is probably good explanation for, or what you can say is that you have lower connectivity and you have at least more shining through nervous system. So it's not, you have not so many connection, and this is probably a hint for the impact of cortisol, which is not an anabolic but a catabolic hormone. So means it destroys connections between the different nerve cells, and this is a fact probably if you are examining the brain of somebody who was severely depressed. And you have, if you're feeling better, you have a higher amount of BDNF and other growth factors, and you have much more connections in the brain, and then you are also feeling better.
Yeah, so chronically high levels of cortisol or hypercortisolemia can wreak havoc in the brain in terms of neuronal atrophy or degradation of nerve cells, like you alluded to, whereas BDNF has quite the opposite effect and can help to lead to increased volume in certain areas of the brain. And I think that's a good segue to the next part, Henning, that I'd love to talk to you about, which is structural changes in the brain as a result of exercise. Mostly we've talked about neurochemical changes, but how does exercise actually change the structure or the morphology of the brain itself?
So the brain is something which is high placid, and that means it changes all the time. When you're here to this podcast, or if you're here to, I don't know, if you're in a church or if you're surfing in the morning, your brain is always changing. And doesn't have to mean that it's really interesting or you enjoy it. Even if you don't enjoy it, your brain is also changing. And your exercise, of course, have a huge impact. And funnily, it impacts mostly an area which is responsible for remembering things. So if you see the face, then remembering the face of your grandmother through all the wrinkles, it's something that is which is given to you by your hippocampus, and this hippocampus has some neurogenesis. So Genesis is something you might think if you're religious or atheist like me. First book of the Bible, the Genesis. So the generation means you have, if you are constantly exercising, you have some more brain cells in your hippocampus, and this is probably the only brain area except for the bulbus olfactorius, which is not so big in the human brain, but there's a huge area in the rodent brain, of course. And in these two brain areas, they detected something like neurogenesis or the genesis of other neurons. I don't know if they saw that you get more astrocytes, so I don't recall this.
Okay. So that's a good starting point, though. So hippocampus, which often, not always, often is observed to be actually smaller, or you see the kind of neuronal atrophy in patients with severe depression again. And then through chronic exercise, we can actually stave off this neural degradation process. So, for example, in older adults, as we age, typically we see neuronal atrophy. But I think, for example, work by Erickson, 2014, people can check out a review of this. Adults who are fit and have exercised for a long amount of time, we actually see a larger hippocampus and more gray matter volume in these areas. So this suggests that chronic exercise can help to increase gray matter volume in certain areas of the brain, i.e. neurogenesis, just like you alluded to in places like the hippocampus.
Exactly. And a colleague of mine, Claudia Völker-Rehage from Münster, I think, which is down in Germany. She made a very nice fMRI study where she compared a control dancing group and fitness group, which did more or less the same intensity than the dancing group, and the dancing group had the highest impact on the hippocampus, so on neurogenesis.
Okay, interesting. Because that's actually interesting you bring that up. I read a recent review. I don't know if you've seen it. Noetel, Noetel, 2024, huge review. Over 200 plus studies on different types of exercise on depression, and there's only about 5 that they reviewed on dancing, but it seems like dancing had the largest effect on depression.
But the study I was talking was not depressant, but normal seniors, old people.
Yeah. I suppose I'm trying to illustrate that I'm just seeing more and more stuff about dancing having quite a large impact on mental health as a form of exercise.
Yeah, but of course it's very difficult to standardize because you just normally had to, you don't know if it's your partner who is very close to you, if it's the music or is it the movements. So to make really standardized, boring study, you just have to have, I don't know, 6 groups there. So,
like a dismantling study would be difficult to run, or a component
yeah.
analysis. Yeah. Okay. So, is there any difference in terms of type of exercise, in terms of the structural changes that we see in the brain? So, what I'm trying to get at is resistance exercise versus aerobic exercise. Do we know whether they have differential impacts on the hippocampus, on neurogenesis, anything like that? What does the evidence say?
Strength exercise is taken as an exercise or form as exercise because they can standardize it towards one repetition maximum. So maximum in strength you can give to one repetition, and so that you can lift one time. And so this is also the same towards endurance exercise. That's why they did the most exercises or exercise studies with endurance exercise and aerobic exercise, aerobic exercise and strength exercise. But what I think is that coordinative exercise has a huge impact. So moving like or doing some stuff I couldn't do anymore, but I would like to do, has probably another impact when you compare it with a normal endurance exercise. For example, the last study we conducted, which is not published yet, but I just finished the data, the statistics. It seems that we have a significant impact on endurance exercise compared with coordinative exercise. That coordination, even if you do it with the same intensity than endurance exercise, that you have the another aim of probably your cognitive outcome is also has an impact. Additionally to your movement, and this probably makes up, I don't know, I just hypothesize this, that you have what we measured, a higher cortisol outcome in these people who are doing the coordinative exercise. So coordinative exercise with the same intensity than endurance exercise leads to a higher amount of cortisol. And this is probably also interesting for for older people, or also for depression, for everything where cortisol probably has an impact. And I think this is many areas. But of course, you have the problematic again that acute exercise is not chronic exercise towards your.
So that those impacts on cortisol are more acutely, you see a higher impact in the coordinated exercise. Yeah. Okay.
What I just referred to was acute exercise. Yeah.
And when you say coordinated exercise, Henning, can you give us an example? Is that like playing tennis or something? Or
No. Do you know what kids do when they jump? They jump, and then we call it the cross. So at the cross, they were just doing this. They were jumping with one leg, and then when they have the cross, they do it with 2 legs, and then they just do it with 1 leg again. And then, of course, something like bouncing a ball, like in basketball, and then maneuvering it through different piles you will have. And yeah.
okay. So yeah, I can see there's an added cognitive element in terms of
Yeah,
coordinating movements,
yeah.
limbs, moving different directions. Yeah,
This is
okay.
also why they have probably so much things they or why they are referring so much to dancing, because this my when I just recall my experiences with dancing, I will recall a high cognitive impact too, because you have to coordinate your steps and stuff. So
Okay. Yeah, interesting. More evidence for dancing potentially. I got to admit though, despite this compelling evidence, or at least preliminary evidence, I won't be taking up dancing anytime soon. So,
yeah.
personally, but yeah. Okay, so we've talked a little bit about the structure of the brain, and we've mentioned this term BDNF, but I don't think we've really dived into it. So, talk to us about BDNF, neurotrophins, just what they are, and why they're so important in the brain.
Yeah, brain-derived neurotrophic factor. They are all novel growth factors which come from different sources in the brain, and of course they are also used in the periphery. In the brain, they are probably responsible for, in my view, for example, something like depression. It's not um, explainable without BDNF, because I think that somehow, of course, serotonin must be involved, and probably it changes the way BDNF can react with structures, and that it can help build more nerve cells or more synapses, and yeah, so I think that brain derived neurotrophic factor is a big thing, but again, it's of course difficult. You just have to distinguish between acute and chronic effects, because if you act acutely, of course, BDNF goes up. But what is happening if you exercise every day? So if you have also structure behind it, that at a certain point you will exercise for the same amount of time with the same intensity every day, and yeah.
Mm. Yeah. Really important point, because I think I've seen mixed findings on the chronic effects of exercise on BDNF. Some pointing to null effects, some pointing to an increase in BDNF. So it's less certain than the acute effects.
When you want to do it really accurate, you have to adapt your training process too, because if you have, for example, the intensity of 70% of the heart rate maximum, and then you exercise for 3 months, then after in the third month, you're probably much more fit than if you haven't trained before than in the first 2 months. And then you are probably higher, have a higher fitness, and then you have to adapt your percentage of the heart rate maximum, for example, where you are exercising with.
Yeah. Mm. So you alluded to something as well there, Henning, about serotonin and BDNF and their relationship. And because,
Hmm?
as I understand it, antidepressants, one of their mechanisms is increasing BDNF, or at least that's an association that we see after antidepressant treatment. You see it promotes more BDNF in people with depression. So potentially a relationship between an interaction between serotonin and BDNF being the mechanism.
Hmm? Yeah, I think so. It's not that it's BDNF alone, unfortunately, but
Or serotonin alone, right?
yeah. not something. At first it was serotonin, and then we replaced it with BDNF. I think that won't make sense, but still, it gets more and more difficult, unfortunately.
Yeah. Well, look, it's we've covered a lot of different mechanisms. I think we've certainly given a lot for listeners and people to think over. Like I said, we'll link a lot of the references we've discussed in the show notes so people can have a look for themselves. But look, as a professor of exercise neuroscience, Henning, I'm curious, what's your overall take on the evidence we have so far, and just on the future as well of exercise neuroscience? Where are the places that we need to go to, the neurochemicals we need to look at more, or the research methods we need to have more certainty in these mechanisms? What's your take?
I would say my take is get the knowledge, or get the most of the statistical knowledge you can get to describe more or less good the reactions due to exercise. And I think that exercise has a huge impact on mental health, and even if it's not completely understandable, or at least, and probably we will never find out how it works. But I think it has an impact, and also if you give standardized exercise, I mean, something what you always have to think: where am I? And what can I reach in the future, which is not reached by others, by other researchers. And then I think even if others researchers probably are smarter than me compared to, for example, in the brain anatomy, and then I probably just have a tool which is exercise, and which I can use in simulating that, and I know how to synthesize this stimulus well.
Yeah, no, that's fantastic to hear your thoughts on that, especially as a up and coming researcher myself, as at the start of my own research career. To hear your thoughts on the future of that, and how someone can make a difference in this field, I think is really valuable to hear. So thank you for sharing that. And I'm curious overall, Henning, is there anything that you would want to kind of share with listeners finally? Anything you want to impart?
Yeah, I
Yeah.
just want to share with you how 10 years ago I was going through Lidcombe and carrying a big box of urine with me to measure my outcome of catecholamines um, per 24 hours. With the 24 hours urine, you all have to collect that, and then you take a small portion out of it, and then you just analyze the amount of catecholamines, and then what do you see?
Mm.
Nothing.
Oh no!
This is like, and
Oh
and
no!
yes, what it's like if you have a bottle which is leaking a little bit. It's also
Oh, jeez, yeah.
not.
Wow, okay. Through carrying a box of urine through Lidcombe. There you go. I didn't think we'd get to that on this podcast. Yeah, well, it's been fantastic to have you on, Henning. Yeah, and I really appreciate you sharing all your wisdom and all the research you've done so far, because, yeah, I've certainly enjoyed reading through all your research, and anyone who's keen to dive into this, I'd certainly recommend your book with Mirko Wegner, which I'll link in the show notes as well. Thanks so much for tuning in to today's episode of the Mental Wellbeing College. If you've made it this far, it means you've gleaned a ton of value from today's episode, or you've fallen asleep. I sincerely hope that it's the former, and if it is, I would be so grateful if you were to hit subscribe, follow, or to share this podcast with someone you care about. Our mission here at the Mental Wellbeing College is to provide a free and accessible resource for people to take action and implement to improve their own mental wellbeing. And you subscribing, following, and or sharing helps us to achieve that mission and to impact people in need. Thanks so much for tuning in. It means a lot. We'll see you next week on the Mental Wellbeing College.